I'm Bob Duhamel, and today we are going to talk about switches. A switch is used to make or break an electrical circuit. Probably the most common use of a switch is a simple on-off switch, so we will draw a simple circuit here. There's a battery. We're going to go to a load, which could be whatever the circuit is whatever the battery is powering. This load resistor represents whatever circuit it is, whether it's a light bulb or a computer, motor, whatever. And we have a complete circuit here with the current running through the load. But how do we stop the current if we want to turn off our circuit? Well, we could disconnect it at the battery, which is kind of a brute force way of doing it. But of course, the most common way is to simply put a switch in the circuit. This is the symbol for what is called a single pole, single throw switch. We'll talk more about those types of switches in a few moments. But this switch in the position it's in now is an open switch. The circuit is broken. There is no current flow. And then if we close the switch, the current will flow. So that's the most common use of a switch. It could also be used in other places, such as in digital equipment. We might have some inputs. This could be either a push button switch or a momentary contact switch, or a more standard switch that once you throw it, it stays that way until you undo it. And so we might have some inputs into a digital circuit where we want to have a 1 or 0 or a high or low, whichever we call it at the moment. We'll talk about those in digital circuits. But we want some inputs here. And so we would have a positive voltage, like positive 5 volts for mini circuits, and have several switches to set different input levels. And there also might be pull-down resistors, which are, in other words, resistors that force these voltages down to a low voltage when they're not switched on, but we'll talk about that kind of thing in digital circuits. But as you can see here, we have our plus 5 volts, and by throwing the switches, that would make this either a plus 5 or a 0 volts, which would be a logical 1 or a logical 0 in this type of digital circuit. So anytime we want to make or break a circuit, we will use a switch. There are different styles of switches to suit the particular application. The earliest switches were what we call knife switches, which are the mad scientist switch that you see in the old like Frankenstein movies that have the knife blade that goes into the contact. These are still somewhat popular in radio applications where you're using twin lead radio transmission lines because they're made to have the proper impedance for twin lead transmission lines. But most modern switches look like some of the examples I have here. This is a light switch or a type of toggle switch because we toggle the actuator up and down. This one is called a bat-handled toggle switch because the handle is shaped like a baseball bat. They can also be cylindrical or paddle-handled. There are different styles depending on what is desired for the particular application. This one is a push-button switch. Here we have a rocker switch. We rock it back and forth to turn it on and off. This one is a mercury switch. We have two contacts, and as it is tilted, the mercury rolls into the contacts and turns on the switch, makes contact between the two contacts. This would be used for position sensors or roll sensors. This is often used in thermostats where there is a bimetallic coil that twists as the temperature changes. There's a mercury switch attached, and when it twists to a certain angle, and that is adjusted by a knob, it twists to a certain angle, the mercury rolls into the contacts and signals the system to either turn on, turn off, depending on whether it's air conditioning or heater. This is a rotary switch. There are different styles of these. Some rotary switches just have one contact, some have many contacts, and some have many banks of contacts that can control many circuits at one time. This is called a dip switch, and that is because it fits into the footprint of a dual inline integrated circuit package. These can have 4 or 6 or 8 little rocker switches, or sometimes they're slide switches, and these are often used for digital input in computer-controlled systems. This is called a magnetic reed switch, and these two reeds or two pieces of metal will contact each other in the presence of a magnetic field. And this is a circuit breaker. It's a special type of switch that will automatically open when a certain amount of current flows through it. And finally, we have here what's called a snap action switch, or more often called a micro switch, but that's actually a brand name. And this type of switch takes a small amount of pressure to actuate a little snap spring that operates a high current contact. No matter what style of switch you have, it may come in one of several different types. The simplest type is the single pole, single throw switch. And this is the schematic symbol for a single pole, single throw switch. It's called that because on one side it has only one connection, and on the other side it has only one connection. It'll become a little more obvious as I show different types of switches what that actually means. And this switch comes in two subtypes. There is a stable contact type, which means if you close the switch, it stays closed, and then if you open the switch, it stays open. But there are also a type called momentary contact, and often they will show a little spring in here to indicate that the switch is spring loaded. This means that if I close the switch, when I let go, it opens again. And that particular type of switch comes in two styles also. We have the normally open, which we show here. The switch is open, we close it, and then we let go, it opens again. And then we also have the normally closed. And we may show a spring up here, may or may not show the spring. Normally closed means that if we leave it alone, it stays closed, and then if we open it, it stays open as long as we hold it open, and then we let go and it closes again. So once again, the simplest type of switch is the single pole, single throw, which is often designated as SPST. Single pole, single throw. Has one connection on one side, one connection on the other side. Now, the next type of switch is called a single pole double throw. What that means is there are two connections on one side. So this would be a single pole double throw, or SPDT switch. So we have one connection on one side, but two connections on the other. So we can designate that whatever's over here, whether it's power or a signal or whatever, if we flip it this way, it goes to this circuit. If we flip it that way, it goes to that circuit. And once again, this can come in two sub-styles. It can be either a stable contact or a momentary contact, meaning it's spring-loaded. So if it's spring-loaded or momentary contact, it would be set up to one circuit, and it may or may not show a spring in the diagram. But whether it shows the spring or not, here we have it connected to one circuit. We push it to the other. When we let go, it goes back to the original circuit. But this is a single pole double throw switch. Next type of switch we'll look at is the double pole single throw. So that has two circuits to begin with, and two circuits coming out, and two switches. So it's two separate switches, but we show a dotted line going between the two switches to indicate that they work together. So there's one handle, two switches. So we close the switch, both switches close. We open the switch, both switches open, and once again this may be a stable contact or a momentary contact switch. So that is a double pole single throw. So DPST, double pole single throw. What's the next style like this? That would be a double pole double throw. So let's show what that looks like. Here we have two poles coming in, separate them enough so I can draw the whole switch. That would be a double pole double throw. So we have two circuits coming in, double pole, and double throw. Each one has two circuits coming out. And once again, it can be either momentary contact or stable contact. Now we're going to take a look at the symbols for push button switches. Here is a single pole, single throw push button switch. Now we don't draw a spring in here under any case, because since it's a push button switch, we know that it's going to be spring loaded unless we have some kind of indication that it latches. In other words, we push it and it stays in, and push it again, it comes out. But push button switch is indicated. Obviously we push down, it makes the contact. So this is a single pole, single throw push button switch, and this one is a normally open switch, which means we push it to close it, let go, then it opens. If we draw the switch slightly differently, this would be a normally closed push button switch. It's closed when we leave it alone, we push the button, it opens, and then we let go and it closes again. You can have push button switches with multiple poles also, but we don't need to go through all of those, and those are somewhat less common than just the single pole, single throw push button switch. And finally, we have rotary switches, which are drawn something like this. We will have a semicircle or full circle of contacts, and then another contact here with a contact that goes between them. So this is a rotary switch that can go to 1, 2, 3, 4 circuits. We can have 2, 3, 4 or more circuits on a rotary switch, and these could be multiply ganged together. So we can draw another one down here. And we would have some kind of indication, a dashed line, that shows that the two switches work in unison. So you may find rotary switches that have multiple gangs of switches, in other words, multiple levels of switches that are all handled by the same shaft. And each one of those levels may have multiple switches on it. So this could be one level of switch, one wafer, if you will, of switch that has two switches on it, all handled by the same handle. And then they may be ganged to have several layers of switches. So you can have rotary switches that have many, many switches, or just a few of them on there. So that is the nature of a rotary switch. Now I've already shown ganged switches, and they are indicated, such as the double pole, double throw. Whenever we gang them, we show them connected by a dotted line, which means that they both actuate together. I'm showing them pretty close to each other here, but it's possible to have ganged switches widely separated in the schematic. So we might have a ganged switch over here, or should I say one of the switches over here going to one part of the circuit, and then maybe another switch way over on another part of the circuit. And these switches work together. So what do? We show a dashed line going between the contacts of those two switches to indicate that those are a ganged switch or ganged switches, and that they operate together. And the last type of switch we talked about is the circuit breaker. The schematic symbol for a circuit breaker looks like a single pole, single throw switch, except it has a little curve over it. And a circuit breaker is a switch that opens automatically when a certain amount of current is exceeded. There are some other things we need to know about switches. One is called contact bounce. So we have our switch. We'll just use a single pole, single throw here. And when we throw that switch, well, we think it makes contact and stays there. But when it makes contact, it doesn't happen all at once. For whatever reason that is, we call it contact bounce. Is the contact really bouncing? Well, it may or may not, but the end result is the same. When we throw that switch, we have our battery over here, let's say, and let's say we have an oscilloscope over here, and we watch that switch go. We see the line down low, and then we may see that voltage go up and down several times before it stabilizes at the higher voltage, and that is called contact bounce. In a lot of situations, we don't care. Switching on a motor, switching on a light, who cares about contact bounce? But how about digital circuits? Let's say this is counting something. Let's say it's a micro switch that has a lever that's counting a cam as it goes by. Well, we want that to count 1 for each time. Well, if we have switch bounce, every time that cam comes by, we might get 2, 3, 4, 1. I mean, I don't know how many times it'll count. So measures have to be taken to mitigate contact bounce in switches. We'll talk about that when we get into digital circuits. Another thing to consider with switches is arcing. You might get arcing with a high voltage circuit. Let's have our switch here, and the switch is closed, and of course there's no resistance here, we just have the current flowing through it. But when we open that switch, if this is a high voltage circuit, we might get enough voltage between the contacts of this switch to ionize the air and cause a spark to jump between them. But you can also get arcing with a low voltage circuit if you have inductance in the circuit. Let's put an inductor right here and draw in a battery just to complete the circuit, and close the switch. And of course, we have the current flowing through the circuit. There's a magnetic field around the inductor, so current is flowing that direction. Whenever you have current flowing through an inductor, you get a magnetic field around it. And when we open the switch, what happens? The magnetic field collapses and continues to push the current in the same direction. And an inductor can actually produce a lot more voltage than the battery that caused the current to flow in the first place. And so that pushes current this direction. We get a lot of voltage and possibly enough to ionize the air and cause a spark here. In fact, that is the way that Henry and Faraday discovered inductance, because they were working with electromagnets, which are simply coils of wire, and they noticed that when they broke the connection, they would get a spark between the switch contacts, and eventually deduced what was happening is that the collapsing magnetic field fed energy into the circuit, kept the current flowing, and put enough voltage across the switch contacts to ionize the air and cause a spark. Now there are two ways to mitigate this. One is by putting a capacitor across the switch. So we'll close the switch, and right now, no matter what current is flowing through it, we have no voltage across here because there's no resistance. To have voltage, we need to have current plus resistance. Well, there's current, but no resistance, so no voltage. So there's no voltage across the capacitor. Now when we open the switch, the magnetic field begins to collapse, and that causes a voltage rise across the switch and the capacitor that are in parallel with each other. And what happens when you change the voltage across a capacitor? When the voltage changes, it first looks like a short circuit. So the current just continues to flow through the capacitor instead of building up across the switch. So it still looks like a short circuit. But as the current flows, the capacitor charges up, and eventually we will have whatever voltage we have here, we will have across the switch. So if this is a 10-volt battery, we'll eventually end up with 10 volts here. But because this capacitor allows the current to flow through it as it charges, it doesn't allow a big voltage to build up across the switch and ionize the air. So the voltage builds up slowly rather than getting a dump of energy across the switch. Another way to mitigate the problem, let's redraw the switch. Is to put a diode across the inductor in this orientation. Now we haven't talked about diodes yet, we will in solid state devices, but all we need to know here is that the diode, when it's oriented one way, is a closed circuit, and oriented the other way is an open circuit. So one way it looks like a closed switch, the other way it looks like an open switch. Right now the current is flowing in this direction, so we're going to have the voltage higher where the conventional current enters the inductor and lower where it exits, just like a resistor. So the orientation across the diode is positive to negative, and with this orientation, the diode looks like an open circuit. Now we're going to open this switch, and what's going to happen? The magnetic field is going to start to collapse. Now the inductor is pushing current in this direction. It now becomes a current source. It looks more like a battery than an inductor. And with a battery or any other voltage source, we have the conventional current coming out, and the side where the conventional current exits is positive and the other side is negative. So that reverses the polarity across the diode. Now this is the polarity where it acts like a short circuit or a closed switch. So instead of building up a voltage here, the current just simply runs through this diode and discharges the inductor without putting any voltage across here. And once the inductor is completely discharged, we simply have no voltage across it at all. We have basically an open circuit, so we have 10 volts here, no volts here, 10 volts across here. So that's two different ways to mitigate arcing across switches. Another consideration with multi-throw switches, and this is very common with rotary switches, where we have a pole coming in and then two circuits on the way out and our contact in between. When we switch from one side to the other, we have a period of time where it's contacting neither one. Well, that may or may not be a problem. Sometimes it might be a problem to have no connection, so we have another type of switch. One is called a break before make, and this is what we have here. So we have the contact, it's on this side, and as it moves, it breaks the circuit and then makes the other circuit. So that is a break before make circuit. But sometimes it's undesirable to have that happen, and so we have a make before break type. And you can see this in rotary switches where we have a couple of contacts. There's one here and one here, and there is a contact on a fiberglass wafer that's being moved between the contacts, and sometimes that contact is fairly small, and as it goes it breaks the circuit before it makes the circuit, but sometimes that contact is fairly wide, and with the wider contact, as it goes across, it will make the circuit before it breaks the circuit. So we have break before make switches and make before break switches, depending on what type we need for a particular application. While we're talking about switches, let's talk about relays. A relay is an electromagnetically actuated switch. The schematic symbol is a coil, which is the electromagnet which operates the switch. And then usually above it will be something that looks like the mechanism, which in this case is a contact and another contact. Let's put some circles on here for finishing the schematic for the relay. And so the way this would work, a simple single pole, single throw relay, when we energize the electromagnet, it will pull the armature down and make contact with the other contact. This is a single pole, single throw relay. It looks a little different from our regular single pole, single throw switch because it's usually drawn to look somewhat like the mechanism inside the relay. But you can have any kind of switch in a relay that you can have in any other kind of switch. So this is a single pole, single throw. A single pole double throw would look very similar. Contact here, an armature, and another contact. And usually this would be drawn as it would be seen in its unactuated state. So now when the solenoid, as the coil is often called, is actuated, it will pull down the armature from the unactuated state to the actuated state. So here we have the single pole double throw. When the solenoid is not activated, it's going to be in this position with the top part of the switch closed, and then when we energize the solenoid, it will pull the armature down to the other contact. And of course we can have any combination of switches. This would be a single ganged single pole double throw. We can have multiple ganged switches, so we can have several. You can see relays with maybe as many as 4 double pole double throw switches in a single relay, or even more. So as many switches as you can actuate with your solenoid you can have on a relay. Common place for a relay is a car, because you cannot pass enough current through the ignition switch, which takes several hundred amps to crank the engine. You can't pass several hundred amps through your ignition switch. So your ignition switch would be connected from your car battery to a solenoid. Of course, this is way oversimplified. And in a car, the relay is referred to as the solenoid. So when someone says, well, my solenoid needed to be replaced, that was actually what we would call a relay in electronics. And so you turn the ignition switch, that energizes the solenoid, and that will usually be a single pole, single throw, so we'll take that part out. It energizes the solenoid, connects here, and now that will connect the battery to the starter motor. And of course, in modern cars, this is often computer controlled, but still a computer gives you maybe 5 volts with a few milliamps out of each output. That's not going to crank your engine, so that would go to an amplifier, to a transistor, which could then operate the solenoid and then crank the engine. And so another place we see relays very often is in computer controlled or digitally controlled equipment, where the digital circuit certainly can't provide enough current for whatever we're actuating, and so that will go to a relay. Sometimes might even have to go to a transistor amplifier to get enough current to even run the relay. But relays are very common. You can hear them clicking here and there wherever they work. When you turn on your ignition in your car, you can often hear relays clicking in many places under your dashboard. So that's a relay. It's just a electromagnetically actuated switch. And for a quick review, we talked about certain styles of switches. Here's a picture of several styles. We have toggle switches, rotary switches, push button switches, rocker switches, mercury switches, dip switches, magnetic reed switches, and a circuit breaker. And we have the different types of switches. We have the single pole, single throw, also known as an on-off switch. We have the single pole double throw, which is also known as an on-on switch because it switches 2 circuits. One is on, then the other one's on. We have double pole single throw, double pole double throw, and then we have rotary switches and push button switches. And whatever type of switch we may have stable contact switches, which you throw them one way, they stay that way. You throw them the other way, they stay that way. And we have momentary contact switches where you push it and it stays in that position until you let go, and then it goes back to the other position. Other considerations we need for switches is, one is switch bounce, and this is especially important in digital circuits. When we throw a switch, it doesn't make a clean contact, and it appears that the contact bounces. So when we go from one voltage to another, it may switch back and forth several times on the way. And in digital circuits, this has to be mitigated in one way or another. Another thing that can happen is switch arcing. This can happen in high voltage circuits or in circuits with inductive loads, and we have to mitigate this arcing across the switch. And finally, we have switches that break the contact before they make the contact, a break before make switch, and other switches that make contact before breaking contact when we go from one circuit to another, which would be a make before break switch. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.